right, hello. Today we're going to talk about Chapter 6, Writing and Balancing Chemical Reactions. Tonight's lecture is a Part 1. Tomorrow night we're going to watch Part 2. In order to start talking about how we balance chemical reactions, we need to first think about what we saw in our modeling experience. What happened in Station 1? Here we have sodium carbonate, and you mixed calcium chloride with it. And you got some sort of a precipitate, but you're not sure exactly what it was that you saw. So what is this precipitate? What? That's what this lecture and what Chapter 6 is all about. It's figuring out what that stuff is. We will also work with balancing and writing equations and classifying them when we get to Chapter 7. Before we get into balancing an equation, I want to take a quick moment to review a few things about compounds. My question for the magnesium phosphate compound down below is this: how many magnesium atoms do you have? How many phosphorus atoms do you have? And how many oxygen atoms do you have? Do you see 3 magnesium atoms? So we've got 3. Now, the 2 on the outside of the parentheses gets distributed into everything in the parentheses. So we have 2 phosphoruses and 8 oxygens. I want to make sure we're very clear on that. If we take a look at the compound itself, we have 3 magnesium ions. That are bonded to 2 phosphate ions. So when you add everything up, you do get 3 magnesium atoms or ions, 2 phosphoruses, and 8 oxygens. Just want to make sure we're clear on that before we move on. This is an important slide for your notes. You need to make sure you write all of this down. So please pause the tape before you listen to the explanation and get everything down. Got everything? Great. First thing, when we balance a chemical equation, we're balancing on paper what we saw in the lab. We're making sure that the law of conservation of mass is satisfied on the paper the way we noticed it was satisfied in the lab. Every one of our stations had mass conserved, and you were able to prove it on 2 out of the 3. The next thing you need to understand is we use something called coefficients in order to balance out our equations. Coefficients are whole numbers that are distributive, and they get put in front of our compounds that are involved in a chemical equation. The subscripts on the formulas of a compound can never be changed. We learned that when we did formula writing. If you change the subscript, you change the chemical compound name and all of the properties. So you cannot ever change the subscripts. Here's a new one. Remember Brinkelhoff. Brinkelhoff is a list of 7 elements that are diatomic when they are in their elemental form. What I mean by that is when they're by themselves, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine are diatomic. Instead of writing bromine as Br, we would write bromine as Br2. Iodine would be written as I2. Nitrogen would be written as N2, and so on and so forth. It's these 7 elements you need to learn that when they are in their elemental form, they are written as a diatomic molecule because that is exactly how they exist in real life. The last thing we need to be mindful of is that we need to know the physical states of our reactants and our products. We use an S for solid, an L for liquid, a G for gas, an AQ for something called aqueous. I don't know if you remember very well, but in station number 1, when we added the sodium carbonate and the calcium chloride together, they were both in solution, meaning they had both been dissolved in water first. So an aqueous solution is a substance that has been dissolved in water. All right, Now, it's time to apply what we learned in the last slide to some real-life examples. We're going to start off with an easy equation, the synthesis of water. Here we have 2 hydrogen atoms bonded and 2 oxygen atoms bonded. When they react, we form water, right? H2O. Now, the problem with this is if we split this into our reactants and our products, we don't see a conservation of mass. We started out with 2 hydrogens. We have 2 hydrogens on our product side, so that works. But we had 2 oxygens and we only have 1 oxygen as a product. We cannot suddenly destroy an oxygen atom. We must account for it somewhere, somehow. So this is what we do. We apply what we've learned from the last slide, and we need a coefficient. If we place a 2 here on our coefficient in front of water, then we end up with a second water molecule right here. So now we've got 2 waters. But what did that do to our hydrogens? You're right. Now suddenly on our product side we have 4 hydrogens. So what do we need to do to rectify that on the product side? Yeah, if we place a 2 coefficient in front of the hydrogen, now we've got a second molecule of hydrogen, and that gives us 4 hydrogens. We have to show that mass is conserved. We cannot create or destroy elements or atoms of any kind. Now, we talked about the fact that these are distributive in the last slide, so let's take a look. If we distribute this 2 here, 2 times 2 hydrogens is 4 hydrogens, which is what we see. If we leave this blank, it's indicated that there is 1 molecule of oxygen, which we see. And then 2 waters is what we should have here, but if we need to look at the atoms, we have 2 times 2 hydrogens is 4, and 2 times 1 oxygen is 2. And if you take a look in the diagram here, that's exactly what we have. We have a total of 4 hydrogens and 2 oxygens. All right, here is our original equation that we started out with from station 1. Sodium carbonate reacts with calcium chloride to produce, let me get the arrow in there, sodium chloride and calcium carbonate. This is what happened. The calcium carbonate is a precipitate. It's insoluble in water. Salt, sodium chloride, is soluble in water, so that stayed inside solution. That's why it looked kind of like a gel, okay? Let's see how we go about balancing that. Well, we're starting off with 2 sodium atoms on the reactant side, but only 1 on the product side. So we need to do something about that. We think to ourselves, 1 sodium times what number will get me 2 sodiums? And yes, you're correct, 1 times 2 will get you a second sodium, okay? But this also gives us 2 chlorine ions over here for the 2 sodium chlorides, okay? So we're going to have to keep that in mind. If we're starting out here with 1 carbonate, then we've got 1 carbon on the reactant side and 1 carbon on the product side. Taking a look at our oxygens, we see that we've got 3 oxygens on the reactant side and 3 oxygens on the product side. Again, of course, we could see them as a single unit of 1 carbonate ion and 1 carbonate ion. It all depends on what you see. If we take a look at our calciums, we have 1 calcium on the reactant side and 1 calcium on the product side. The only thing we haven't accounted for over here are the chlorines. On the reactant side, we have 2 chlorines, and on the product side, because we put the 2 coefficient in right here, we also have 2 chlorines. So when we take a step back and we split the equation down the middle with our reactants on the left side and our products on the right side, we have the same number of atoms on both sides, simply by placing a 2 coefficient in front of the sodium chloride. Alright, let's take a look at our third example here. Here we've got calcium sulfate reacting with aluminum bromide to produce calcium bromide and aluminum sulfate. If we start counting, we have 1 calcium on the reactant side, 1 calcium on the product side, 1 sulfate on the reactant side, but 3 sulfates on the product side. So in order to rectify that, we need to place a 3 coefficient in front of the calcium sulfate. That will distribute in and not only give us 3 sulfate ions, but it will also give us 3 calcium ions. Now again, if you are not very adept at looking at the polyatomic ions, then we can look at it from an element standpoint. And we've got 3 sulfurs on the reactant side, and this over here on the product side, that subscript distributes in, and we have 3 sulfurs on the product side. We now have 12, let me draw that arrow again, 12 oxygens on the reactant side, 3 times 4, and over here we've got 3 times 4 oxygens is 12. So it's balanced either way you look at it. The aluminums, we've got 1 aluminum on the reactant side and 2 on the product side. So we've got to squeeze in a 2 coefficient here in front of the aluminum bromide. That now gets distributed, and we have 2 aluminums, but now we have 6 bromines. On the product side, we have 2 bromines. So we have to think to ourselves, 2 times what will get me 6? Well, 2 times 3 gets you 6. This now gets distributed. So we have 3 calciums, because 3 times 1 is 3, and 3 times 2 is 6 bromines. And we are balanced. One thing I want to take a minute here and talk about are parentheses and how we handle them. We didn't need to worry about a coefficient in this example in front of the aluminum sulfate, but let's just say, for instance, that we did need to worry about it. So I'm going to write down here the aluminum sulfate one more time. Let's say that we needed for some reason to place a 2 here. How does that work for us? Well, we have to distribute the 2 to everything. So we have 4 aluminums as a result, because 2 times 2 is 4. Now keep in mind here that this 3 on the outside of the sulfate means that we have 3 sulfurs, but we have to multiply it by 2 as well. So we have 3 times 2 sulfurs is 6 sulfurs. For the oxygen, we have 3 times 4 is 12 oxygens, and 12 times 2 is 24 oxygens. Another way to look at this is if we needed 2 aluminum sulfates, we would have to write Al2SO4 3 twice, right? So if we add everything up this way, we still come up with 4 aluminums. When we distribute this 3 in, we've got 3 sulfurs and 3 sulfurs, which gives us 6 sulfurs. And 3 times 4 is 12 oxygens, and 3 times 4 is 12 oxygens, which gives us 24 oxygens. So parentheses just add an extra step in terms of distribution and multiplying, but it's not any more difficult than any other problem. We're going to continue working with this in class, and I'm going to let you guys work on a problem set in class with me tomorrow, so you guys will get some practice in front of me where you can ask me all the questions you want. Have a great night.